G'day and welcome to part 2 of the applications for finding the minimums and maximums in calculus. In the previous video we looked at finding the maximum volume of a kid's swimming pool given a particular piece of canvas. In this case we're going to look at a race that starts out some point along in the water and ends up on land somewhere. So if I give you a little diagram of what's happening, somewhere we start out here like on a pier or something, out in the middle of the water, and then this is the beach line along here, and we've got a finish line over here. Okay, so that's the start and the finish. Let's just read the question and hopefully that'll make sense. So Joseph is competing in a surf lifesaving competition race. He's standing on a long narrow point of land which juts out 5 kilometers. That's this one here. 5 kilometers directly opposite a surf club, and the finish line is 8 kilometers along the shoreline. So that one there is 8. If Joseph can swim at 7 k's and run at 16 k's an hour, find the position along the shore that he should aim for in order to minimise the time taken to complete the race. So I guess he's got a couple of different options here. He could swim the entire way along, which would be all the way down to there. He wouldn't bother swimming any further than that because it would take longer, but he can swim at 7 k's an hour, and he can run faster than that, obviously, because people can run faster than they can swim. So I guess another option he could have is to swim directly into the bank, which would be 5 k's, and then run 8 k's. But I guess what we could explore is there some point along the beach that he could actually kind of swim towards, which would give us the minimum time taken for this race. I'm going to suggest that this point along here is actually a very long way of going about it, and this one here would be not equally long, but this one also be a longer one as well. I think somewhere along the line here it'll actually be better for him to go to a point there, swim to a point there, and then run the rest of the race. And that's essentially what we're trying to find. At what point along the bank is he best to do this? So what I need to do is find out first of all the distance that he needs to travel. Okay. If I say that he swims along to a point here, I'm going to call that point X. Okay, so he swims out to a point X, and then swims along the beach to the point X, and then he gets out and runs for the rest of the time. So I can tell you that the distance that he runs will be 8 minus X. Okay, because it's this distance here, the whole distance minus that distance there, so that'll be 8 minus X. To work out how far he swims, we simply use Pythagoras, 5 squared plus X squared, and then get the square root of that. So I end up getting something that looks a little bit like this. The distance is going to be the square root of 5 squared plus X squared plus 8 minus X. Now I need to work out the time taken, because I want to find the minimum time. I don't want to find the minimum distance, I want to find the minimum time, or the minimum distance that gives the minimum time. So what I need to do is I need to find an equation that groups speed, distance and time all together, so then I can find the minimum time taken. Now I know that the speed is actually a function of distance divided by time. Okay, but I don't want speed, I want time, the time taken. So I can tell you that the time taken will actually be distance divided by speed. Just rearranging that equation, I get distance divided by speed. So I'm going to say that he swims this distance, square root of x, 5 squared plus x squared, divided by the speed that he can go at in the water, and that's 7 k's an hour, so 1/7 times that, plus he has to run 8 minus x kilometers, divided by the speed that he can run at, which is 16 k's an hour. So 8 minus x divided by 16, or 1/16 times 8 minus x. So this is my function, and this is the hardest bit. Once you get to this point, it's relatively straightforward from here. But this bit is the most tricky, finding that equation. So you can have a look at the way that I did this, and I think there's also another example in your textbook about oil pipelines, which is very, very similar. So now I'm going to get the minimum time, so I'm going to differentiate this with respect to x. Okay, this can be a little bit tricky, but it's just using our skills that we learnt from chapter 5. So I'll let you kind of do that if you want to, but this is the way that I went about it. I multiplied everything by a half, and then I multiplied by the derivative, which is 2x. So therefore I ended up getting this function here. Okay, now I need to find the minimum time, so I'm going to make the derivative equal to 0. So I get 1/16 equals all of this stuff here. And then what I'm going to do, I'm going to multiply, I'm going to get rid of the fraction, so I multiply everything by 7. I'll get rid of the fraction on the right hand side, sorry, and so I multiply everything by 7 and I get this equation here. Now I've got a problem because I've got a square root sign in there, and I want to get rid of that square root sign, and I can now because that's the only thing on the right hand side. So I'm going to square everything, and I end up getting 256, which is just 16 squared, x squared over 49 equals 5 squared plus x squared. And then I can just simply rearrange for x squared. I can minus 1x squared on both sides, and I get 207x squared over 49, because 256 over 49 minus 49 over 49 is 207x squared over 49, which is equal to 25. Multiply 25 by 49 and I end up getting something else, and then divided by 207, and I end up getting x squared equals 5.918, so x equals 2.43. Let me just show you this all on a calculator. So I'm going to get a new calculator screen, and I'm going to put in my equation, which was a seventh 1 over 7. What I might do is I might put all of this in, and then come back. I'll pause it and put all this in and come back. Okay, so there it is. Now again, I can put a restriction on this. I know that x cannot be bigger than 8, because if x is bigger than 8, I actually go past the point, and so I swim past the point and then have to come back to it, and it's a waste of time doing that. And I know that x actually has to be bigger than 0. Okay, because if x is less than 0, he's actually swimming the wrong way and then having to run further. So I can put a restriction on this that x needs to be between 0 and 8. Okay, and I can put that in. And so this is my graph. Okay, now as you can see, if x is equal to 8 over here, let's go back to have a look at this one. If x is equal to 8, that means that he's swimming the entire way, and so it takes him that long. If x is 0, that means that he swims perpendicular to the beach, and then straight into the bank, and then he runs the entire length of the bank, and so that's there as well. You can see that swimming is a little bit slower than it takes a little bit longer than I guess swimming and running, but there is going to be some sort of minimum along here as well. So I'm going to find out that minimum point, and it will be somewhere along here. And there we go, 2.43, which is what I had before. So I can tell you that if he aims at 2.43 k's along the beach, so somewhere along here, 2.43, that's about there, he will complete this in 1.14 hours. That's how long it will take him to complete this race. Okay, so that's how we go about doing that kind of question. That question has come up a lot of times in a lot of exams and a lot of SACs that I've seen in the past. So make sure that you do understand that kind of question. I think there's a few more in your textbook that are like that, and then you can always ask me for more questions like that as well. So I feel like the hardest bit of this question is actually finding the equation. Once you've got the equation, I mean, sure, the calculus is a little bit tricky, all of the skills and stuff like that, but it's not too bad once you get the hang of it. So finding the equation is the hardest bit. Once you've got that, it should be all straightforward. So thanks for watching. In the next video, we'll look at related rates. Thanks.